Young's double slit experiment. In the previous lecture, we have seen the formula for the path difference at any point P on the screen, which is at a distance of y from the center of the screen and angular position theta. Now let's have a quick recap. See, when you make the setup of Young's double slit experiment, in the short form you can say YDSE. So we have the screen over which the fringes or the bands will be formed. Then we have two slits, say S1 and S2, and there is a main source of light. We have seen in the model we have taken small d as the distance between the slits and capital D as the distance between the slits and the screen, remember? Then suppose there is a point P on the screen, any point P. So P is identified by two parameters. One is the position of P, or you can say the distance of P from the center of the screen. This is the center of screen, and we have also seen that maxima or bright fringe is formed at the center of the screen. So this point is also the central maxima, isn't it? You can also say this point as central maxima or the central bright fringe. So we can define a point with respect to this central point, say by a distance y, okay? And if you join this point, the center of the slit, say C, I'm marking the center of the slit as C, and I'm making a line joining C with P. So this will define the angular position of the point P, okay? So basically there are two parameters. One is the angular position of the point on the screen, which is angle theta, and another is the position or linear distance, or simply the distance of the point from the central of the screen, which is y. Got it? If you take different points on the screen, both theta and y will be changing. For different points, we will have different theta, we will have different y, and we have seen this is the reference line for measuring theta. Above this line, theta will be positive, below this line, theta will be negative, and this is the origin, the central of the screen. Above the origin, y will be positive, and below the origin, y will be negative. Then we have derived the formula for the path difference in terms of the angular position theta. So we have seen if there is any point P on the screen whose angular position is theta, and if the lights are reaching there from slit 1 and slit 2, correct, and this distance is y. So we have seen some of the formulae which we will have as FTPs, fingertip points. The path difference came to be d sine theta, number 1. The value of tan theta is y by d, number 2. Number 3, for maxima, we have the angular position as n lambda by small d, where n is of course an integer, and y is equal to n lambda capital D by small d, right? N will tell you the order of the maxima. Like for mth order maxima, n will be equal to m. Like for the first order maxima, n will be 1. For the second order maxima, n will be 2, so on. For minima or the dark, maxima is a bright fringe, minima is a dark fringe, maxima is the bright band, minima is the dark band. Theta is equal to what? 2n minus 1 lambda by 2d, and your y came to be 2n minus 1 lambda capital D by 2d. Okay, so these are the angular position and the distance of minimas. Then we have seen the fringe width, the bandwidth, beta, the formula was lambda capital D by small d, and the angular separation, that is the angular width between two consecutive maxima or two consecutive minima, this will be lambda by small d, correct? So these are some of the formula which you will keep on fingertip for solving the problems. Okay. Now in today's lecture, we will be applying this formula for solving some of the numerical exercises. Now see the first problem. In Young's double slit experiment, the angular width of the fringe is found to be 0.2 degree. So you are given the angular width as 0.2 degree, okay, on a screen kept 1 meter away. You know, these are the slits and this is the screen, and always remember the standard symbol. Capital D is the distance between the slits and the screen. So capital D is 1 meter. The wavelength of the light is 600 nanometer. What will be the angular width of the fringe if the entire setup is immersed in water, okay, and you are given the refractive index of water? So basically in this problem, what is the goal? The experiment is performed in air, okay, and you are given the angular width. Remember, today we have seen the formula for angular width. Angular width is the angle between two consecutive maximas or two consecutive minimas. So the formula for angular width is lambda by d, okay. The formula for angular width is lambda by d. Now, if you are changing the medium of the setup, suppose the whole experimental setup is kept in water or oil, what do you think? Will there be any change in d? D is the distance between the slits. Small d denotes the distance between the slits. It will remain the same. But will lambda be changed? Yes. Lambda, because lambda depends on medium. So if you are changing the medium, the wavelength will change. The wavelength of light used in Young's double slit experiment for interference, the wavelength will change. And if there is a change in the wavelength, so of course your fringe width will change. So say we know the formula we have seen in ray optics. Wavelength in the medium is the wavelength in vacuum divided by refractive index of the medium. Remember the formula? In any medium you can write the wavelength will be the wavelength in vacuum divided by the refractive index of the medium. So you can write the fringe width in the medium is what? The wavelength in the medium divided by d, isn't it? The wavelength in the medium divided by d. What will be the wavelength in medium? Wavelength in vacuum divided by refractive index into d. Okay, and what we can write? Wavelength divided by d. Can I say this will be the fringe width in vacuum? So therefore you can write the fringe width in the medium is equal to the fringe width in vacuum divided by mu. So we got the formula which relates the fringe width in the medium with the fringe width. Of course, right now we are talking about angular width. There is also the linear width beta. This is for angular width. Same relation will be for beta because wavelength will have the same relation. So the angular fringe width in the medium is the angular fringe width in vacuum divided by mu. So therefore the angular fringe width in the medium is, what was the angular fringe width in the vacuum? 0.2 degree. And you need not to change the unit from degree to radian because it's the division. So if you are taking it in degree, answer will come in degree, and if you keep it in radian, answer will come in radian divided by what is the refractive index? 4 by 3, so I'll get 4 into 3, so I'll get 0.2 into 3 by 4, 0.2 into 3 divided by 4, so I'll get 0.15 degree. That is the answer. So this will be your angular fringe width in the medium. Got it? Now see the second problem. In Young's double slit experiment, the angular width of a fringe formed on a distant screen is 0.1 degree. The wavelength of light is 6000 angstrom. What is the spacing between the slits? So in this problem we are given the angular width as 0.1 degree. The wavelength is 6000 angstrom and we have to find the distance between the slits. Okay, we know the distance between the slits is written as what? Small d. So see, we know the formula for angular width. that is lambda by small d. So it will imply that d will be lambda by the angular width. Very simple. But see, when you are writing in this formula, when you are putting the values, you have to make sure everything is in the SI coordination. Correct? So lambda must be in meter, d will come in meter, and this must be in radian. So you have to make sure that it must be in radian. Now you might have a confusion कि sir, in the previous problem when we were doing, we haven't converted it into radian. See, in this problem, in the previous one, there was the involvement of angle on both LHS and RHS, okay? And you know, when you convert angle from radian to degree or from degree to radian, there is a multiplication conversion. So if you are converting this by some multiplicative factor, same multiplicative factor will be on LHS. So it won't make any difference overall. So if you are keeping it in degree on RHS, your answer on LHS will come in degree. And if you keep this value in radian, then on LHS also you will get the answer in radian. So what we did, we kept the vacuum width in degree. So in the medium width also has been reported in degree. But in this equation, we have d, lambda and angle. So you must have the SI coordination. So we will convert the angular width 0.1 degree into what? Radian. And we know 180 degree is pi radian. So therefore 0.1 degree will be pi divided by 180 into 0.1. This will be your conversion into radian. Now what will be the distance between the slits? Lambda is 6000 angstrom, that is 6000 into 10 power minus 10 multiplied by pi into 0.1 into 180. So we will have the answer as what? Let me calculate. You will have the answer as 6000 exponent minus 10 into 180 divided by 0.1 divided by pi. You will have 3.437, that is approximately 3.44 into 10 power minus 4 meter. So this is the distance between the slits, okay, small d. Got it? Okay. Now see the next problem. In YDSC Young's double slit experiment using monochromatic light of wavelength 600 nanometer, interference pattern was obtained on a screen kept 1.5 meter away from the plane of two slits. Calculate the distance between the slits. If the fringe separation or fringe width was found to be 1 millimeter. So what are the given parameters? You know, this is your screen, this is capital D, this is slit 1, this is slit 2, this is small d. So we are given wavelength 600 nanometer, that is 600 into 10 power minus 9 meter, correct? This is the wavelength. Then we are given capital D, the distance of the screen from the slit 1.5 meter, and you are given the fringe width or fringe separation or bandwidth beta, that is what? 1 millimeter, that is 1 into 10 power minus 3 meter. Now if you remember the formula for bandwidth, the bandwidth is lambda capital D by small d. So therefore small d will be lambda capital D by beta. So what is lambda? 600 into 10 power minus 9. What is capital D? 1.5. What is fringe width? 1 into 10 power minus 3, and you will get the SI system unit meter. So your answer will come to be 600 exponent minus 9 into 1.5 divided by 9 into 10 power minus 4 meter. This will be your answer. Got it? Now see the next problem. In the given figure, the positions of the first bright fringes B1 and B2 on either side of the central bright fringe O in Young's double slit experiment. So we can see two bright fringes. If you remember the previous lecture, we have seen in Young's double slit experiments, maximas are located symmetrically, remember? So if this is 1 millimeter and this is first maxima, above the central maxima or center of the screen, then exactly below 1 millimeter we will also have first maxima, isn't it? And you know the maxima, the position of maxima is given by the equation lambda capital D n by small d, and will be the number of the maxima, the order of the maxima. So in this case we have one first maxima B1 here and one first maxima B2, and B1 is, you can see, exactly in front of slit 1 and B2 is exactly in front of slit 2, and this is given to be 1 millimeter. So in the figure, can I say D is 1 millimeter, yes or no? Say. Can we say small d? What is the small d in the standard model? The distance between the slits, that is 1 millimeter, correct? Now what will be, say this distance is y, B10, B10 is y, okay? So can I say y will give you the position of first maxima? So you can write y is equal to n lambda capital D by small d and put n is equal to 1, because we are talking about the first maxima, so it will come to be lambda d by small d, isn't it? Okay. What will be the distance B1 and B2? So B2 is also the first maxima, and maximas are located symmetrically. So if this is y, this whole distance will be what? 2y, isn't it? So your B1, B2 will be 2y, that is 2 lambda capital D by small d, correct? Now what we need to do, we can equate 2y with small d. From the figure we can say B1, B2 is same as S1, S2. So it will imply that 2y is equal to what? Small d. So you will get 2 lambda capital D by small d is what? Small d. And what we have to find? We have to find the wavelength of the light. Make lambda as the subject. So lambda will come to be d square by 2 times of capital D. And what is small d? 1 millimeter. So we'll get 1 into 10 index minus 3 square divided by 2. And what is capital D? 1 meter. So we'll get the answer as what? 5 into 10 power minus 7 meter. Okay, this will be the answer in meter. Now if you want to write the answer in angstrom, so you know 1 angstrom is how much? 10 power minus 10 meter. So simply divide by 10 power minus 10. Whenever you need to change x meter into angstrom, divide by 10 power minus 10. So wavelength can also be written as 5 into 10 power minus 7, 10 power minus 10 angstrom. So it will be 5 into 10 power 3 angstrom, that is 5000 angstrom will be the answer. If it is not given, if you are doing the subjective problem, you can also leave answer in meter. But suppose if it is demanded in the problem that give your answer in angstrom or give your answer in nanometer, then you have to convert. And always remember, when you are changing meter in angstrom, divide by 10 power minus 10. If you are changing in nanometer, divide by 10 power minus 9. Okay? Your answer will come in nanometer, your answer will come in angstrom. Okay? So this will be the answer for this problem. Now see the next problem. The distance between the first and the 6 bright fringes formed in Young's double slit experiment is found to be this much. Now you are given the distance between the first and the 6 bright fringes. So first bright fringe will be formed somewhere like this here. This is the center of the screen. And 6 bright fringe will be formed somewhere here. And say this is the distance delta y. Okay. So you are given this delta y as how much? 12.5 5 millimeter, and the distance between the slits separation is 0.12 millimeter, and the distance of the screen from the slit is 60 centimeter. First we have to find the fringe width, and then we have to find the wavelength of the light. Okay, now let's see how we can proceed. Just think, you are not given the position of the first bright fringe or the sixth bright fringe. Instead you are given the gap, the distance between the sixth and the first bright fringes. You know, for mth bright fringe the formula is m lambda capital D by small d, isn't it? So we can write, therefore for the sixth bright fringe the position will be m is 6 lambda capital D by small d, and for the first bright fringe m will be 1, so it will be this. Now we can find the distance between the sixth bright fringe and first bright fringe, say delta y, as y6 minus y1. So I can take lambda d by small d as a common factor. So I'll get 5 lambda capital D by small d, correct? And this information is given that this distance between sixth bright fringe and first bright fringe is 12.5 millimeter. So it implies that 5 lambda capital D by small d is 12.5, and I am changing it in meter. Okay, so we got this equation for this quantity, 5 lambda capital D by small d. Now the first part of the problem demands the fringe width or the bandwidth. So the bandwidth has a formula lambda capital D by small d. Okay, so when you need to find the bandwidth, is it possible? We don't know lambda, we don't know d, we don't know small d individually. Okay, all these three values are unknown individually, but we have this combined value, so you can know the fringe width. So see, in this data, we suppose we are not putting the value of lambda capital D or small d, and we are just making lambda capital D by small d as the subject. So it will come to be 12.5 into 10 power minus 3 meter divided by 5, isn't it? So it will come to be 12.5 divided by 5, that is 2.5 into 10 power minus 3 meter. So this value is coming for which quantity? Lambda capital D by small d, and I can also write as millimeter, 10 power minus 3. Okay, so this is what? This is the fringe width. So therefore fringe width is 2.5 millimeter. That is the answer to part A. Can you see, we just got the value of the fringe width. We need not to get worried what is the value of lambda, what is the value of capital D, what is the value of small d. No, this equation is telling you, you can get this whole term as the subject, and you can get its value, which will directly give you the fringe width. But in the second part, we have to find what? The wavelength of the light. Okay, now I guess you can do the second part yourself. We got the fringe width. Now we have to find the wavelength. So we know the formula for fringe width is what? Lambda capital D by small d. The wavelength will be fringe width into small d by capital D. Now you are given capital D, you are given small d, put everything in meter, you will get the wavelength. Okay, this I guess is the straight calculation, straightforward, which can be done by you. Now see the next problem. In Young's double slit experiment, the slits are this millimeter apart, and the interference is observed on the screen placed at a distance of 100 centimeter from the slits. It is found that the ninth bright fringe is at a distance of 7.5 millimeter from the dark fringe, which is second from the center of the fringe pattern. Now understand the problem. Let me make a freehand schematic figure. This is the screen for obtaining the interference pattern. We have two slits. The distance between the slit is a small d. This is capital D. Okay. Say this is the position of ninth bright fringe. Okay. So bright means maxima. So for this, say this has a coordinate or position y9, and this is the center of the screen or the central maxima. So for this, you will put the formula for maxima, that mth maxima is m lambda capital D by small d. So y9 will be, put m as 9 lambda capital D by small d, isn't it? Okay, let it be equation number 1. Got it? Now say we have another point on the screen. This is point A and this is point B, and this is the second dark fringe. Dark fringe means minima. Second dark fringe, that is minima, and say its coordinate or position from the center of the screen is y2. Remember, this is minima. For minima, for mth minima, the formula is 2m minus 1 lambda by lambda capital D by 2d. Remember, the formula gets changed for minima. So the coordinate of this minima will be, m will be how much? 2. We are talking about the second minima. 2 into 2 will be 4. 3 lambda capital D by 2d. So this is your position of the second minima, correct? Okay. Now what will be the distance between them? So you will say the distance between them will be this, say delta y. So delta y will be y9 minus y2. So delta y will be 9 lambda capital D by small d minus 3 lambda capital D by 2d. So you can take lambda capital D by t as a common factor. 9 minus 3 by 2. So you'll get lambda capital D by small d. 18 minus 3 by 2, that is 15 lambda capital D by 2d, correct? So this is the distance between these two fringes. Now you are given the value of a small d. The distance between the slit is how much? 0.589 millimeter. And capital D, the distance of the screen from the slit is 100 centimeter, that is 1 meter. And we have to find the wavelength of the light, isn't it? So you are given this delta y, the distance between the ninth maxima and the second minima, as 7.5 millimeter. So put it as, so we will have, what is your delta y? 15 lambda capital D by 2 small d is 7.5 millimeter, means 10 power minus 3 meter. Make lambda as the subject. So it is 7.5 into 10 power minus 3 into 2 into d divided by 15 into capital D, isn't it? Now let's put all the values in SI system. So lambda will come to be 7.5 into 10 power minus 3 into 2, and d is given to be 0.589 millimeter divided by 15, and d is given to be 1 meter. Answer will come to be in meter. So lambda will come to be 7.5 index minus 3 into 2 into 0.589 exponent minus 3 divided by 15. So 5.89 into 10 power minus 7 meter. This is the answer. This is the wavelength of the light used in YDSC of this problem. Okay, if you want to give your answer in angstrom, divide by minus 10, so you'll get 5890 angstrom. If you want to give your answer in nanometer, you can divide by 10 power minus 9, so you'll get 5.89 into 10 minus 9. When you divide by minus 9, 10 power 2 will come in the numerator, nanometer, or 589 nanometer. If it's a subjective problem and there is no specific demand for the unit, you can leave your answer in meter. Now see the next problem. Young's double slit experiment is first performed in air and then in medium other than air. it is found that 8 bright fringe in the medium lies where 5th dark fringe lies in the air. What is the refractive index of the medium? So see, of course there will be change in the wavelength if you are using the same light, same setup, no change in small d, no change in capital D, but wavelength will change, correct? So we know the bright fringe, for mth bright fringe we have the formula lambda capital D m by small d, isn't it? So in the medium we have the 8 bright fringe. So let's make two equations, okay? First I am writing for medium. So we have the 8 bright fringe in the medium. So it will be 8 capital D lambda of medium divided by small d, isn't it? We have to specify the lambda because lambda will not be same in air and in that medium. And for air, it's the 5th dark fringe. So dark fringe has the formula. For mth dark fringe we have 2m minus 1 lambda capital D by 2d. So we will apply this formula and m will be what? 5. So 10 minus 1, 5 into 2, 10, 9 lambda of air capital D by 2d, isn't it? So this will be the position of the 5th dark fringe in air. Now according to the problem, both have the same position. So it implies that y8 in medium is same as y5 in air. So we'll have 8d lambda of medium divided by d is 9 lambda of air capital D by 2d. Now d will get cancelled away, capital D will get cancelled away. And can I write, you remove the basic relation, lambda of the medium is lambda of air divided by refractive index. So therefore 8 lambda of air divided by mu is equal to 9 lambda of air divided by 2. Lambda of air will get cancelled away and mu will come to be 8 into 2 divided by 9, that is 16 divided by 9. So we'll get 1.77. Your answer will come to be 1.77. This will be your answer. Okay, simply you are applying the formula for the medium, which is approximately round off value will be 1.78. So simply you have applied the formula for 8 maxima in the medium, keeping the wavelength as lambda of the medium, 5th minima for the air, keeping the wavelength of lambda of air, and then you equate both the things, then you related the wavelength. Okay, so this was the lecture where we have done some of the numerical problems on Young's double slit experiment. Now in the next lecture also we will be proceeding with more of the problems where we will see if multiple wavelengths are used, then how the maximas or minimas will coincide. Okay.